Hello. Today we're going to look at the Doppler effect, in particular the Doppler effect in sound, or more accurately the Doppler effect with relatively slow moving waves. Come back to that in a minute. So Doppler effect is the last part of a wave phenomena topic, and we'll be splitting it into two subsections, in sound and in electromagnetic radiation. And these are the understandings and the skills as listed in the current version of the DP Physics Guide. A couple of equations down there at the bottom that we will be using today. So, the Doppler effect is illustrated by this video. I don't know if the sound's going to be picked up very well here, but it goes something like this. So you may well be familiar with the experience of a vehicle making a noise, going past, and it approaches with a relatively high pitch and then moves away from you with a relatively low pitch. So something like this, as the tradition has it. That change in pitch is only experienced by the observer. From someone sitting in the car, the sound will be of a constant pitch, and the pitch that is experienced by the person sitting in the car would be between the higher pitch experienced by the observer for the approaching car and the lower pitch experienced by the stationary observer for the departing car. The reason behind this is because the sound waves are travelling out, and every period, every so many seconds or fractions of a second, a new wavefront is going out. But those waves travel out, sound waves travel out at the speed of sound, so approximately 330 meters per second. And yet the source of those waves is moving, or in another situation, maybe the observer is moving. Both of these situations will result in a version of the Doppler effect. Coming in, higher pitched, moving away, lower pitched. Now, to illustrate what's happening in the Doppler effect, we can use this particular website. So I'm going to see if I can just switch over to showing you that website. If you give me a second. Not done this very often. Right. Here we go. So, what do we see here? Here we have at the bottom of the screen there a source of waves, and in the middle, or just to the left of my little picture there, in fact, let me take me out of the picture. There you go. So we can see a little ear thing, which indicates the observer. If I press play, then the source of waves is moving along. And let me just pause it. And so it's emitting a wave. It's actually emitting a wave every second as it moves. And those waves are travelling away. But the source itself is travelling a significant fraction of the speed of the waves. And therefore, in front of the source, those waves get compressed. They get squeezed closer together. And from the perspective of the observer, they'll encounter no sound at all until that first wavefront appears, and then lots of waves in short succession, in other words, a high pitch, followed by the waves spread out, so much more infrequently, in other words, a low pitch. That's what happens with a stationary source and a moving source and a stationary observer. If, on the other hand, we change that around, we can have a moving observer and a stationary source. So now you'll see the ear has moved over to the left hand side and our source is in the middle. Let me press play. So again, once every second, you pause it. But now our observer is moving into the waves, so again it'll experience that waves of a greater frequency until the observer passes the point at which the waves, and now it's moving sort of with the waves further away, so it takes, there's a longer period, a longer time between the observer experiencing those wave fronts, which means you have a lower frequency. Let me move back to the slideshow. Put me back there as well. So there's the that's the website if you want to go and have a go at this yourself. So it's a great little applet that is. And go back to the PowerPoint. So there's kind of four situations. Situation number one is a source moving towards the observer. So those waves will compressed if compared to the non-moving source. So the observer will experience a higher frequency and a shorter wavelength. On the other hand, when the source is moving away from the observer, the wavefronts are more separated compared to the non-moving source. The lower frequency, then less waves will be arriving per second at the observer, and therefore a longer wavelength, a lower pitch. Now, I'm not going to go through the derivation of the equation, but this is the equation for the observer. Just move that around, put that around. Make myself a bit smaller. There we go. So this equation is the equation you use if you have a stationary observer and a moving source. And before you ask, if you have a moving observer and a moving source, it's a little bit more complicated, but we don't need to worry about that, because at the IBDP physics level, even at high level, you're stuck with just a moving source or a moving observer, not both. So for a moving source, this is the equation you use. F prime, which is the frequency as measured by the observer, equals F, the frequency as measured by the source, divided by, and then it's a ratio of the velocity, the speed of a wave, over the speed of a wave plus or minus the speed of the source. Now, which plus, whether you use a plus or whether you use a minus, depends on whether the source is moving towards the stationary observer, minus, or whether it's moving away from the stationary observer. This is a bit tricky, because the data booklet will give you this equation. In fact, it even identifies the equation as a moving source equation. So you don't need to remember that. But you do need to remember that minus in this case is source away from observer, and positive is source moving, minus is source moving towards the observer, and positive is source moving away from the observer. Right, the other two situations that you might encounter are the ones where the observer is moving. So observer moving towards the stationary source, shorter period between the wavefronts, therefore higher frequency, shorter wavelength, higher pitch. And if the observer is moving away, as we saw when we looked at the video, then there's going to be a longer time between the wavefronts being observed by the observer, lower frequency, lower pitch sound. The equation for the moving observer is very similar to that of a moving source, but it's not quite the same. It's sort of flipped over, and again, although it's given to you in the data booklet, you have to remember that in this case the minus sign is the observer moving away from the source, and the plus sign is the observer moving towards the source. Confusing, I know. But there you go. So those are the two equations that we have to recall, and it really just is a question of identifying the situation, working out, hey, this is a Doppler effect equation, and if you know it's a Doppler effect situation, then have you got a moving source or have you got a moving observer? And is the source moving towards or away from the stationary observer, or in the case of a moving observer, is the moving observer moving away to or from the stationary source, and therefore do you use a plus or minus, and that can be a bit of a pain to remember, but that's what you've got to do. Okay, thank you very much for your attention. Next video we will look at a couple of examples of IB questions using these equations.